There is a moon orbiting Jupiter that almost nobody talks about. Not Io, the most volcanically active body in the solar system, its surface constantly being remade by hundreds of active volcanoes, yellow and orange and red from sulfur compounds, so geologically young that impact craters barely exist because the lava fills them in before they can persist. Io is dramatic. Io demands attention. Not Europa, the smooth, icy moon with the cracked surface that looks like a broken eggshell, the one with the confirmed subsurface ocean of liquid water, the one that appears in every discussion of where in the solar system we might find life, the one with missions specifically designed to visit it and search for biosignatures. Europa is scientifically compelling in an immediately obvious way. Europa gets the headlines. Not Ganymede, the largest moon in the entire solar system, larger than the planet Mercury, the only moon known to generate its own magnetic field, itself confirmed to have a subsurface ocean and recently shown by the Hubble Space Telescope to have auroras driven by that magnetic field. Ganymede gets attention because of its sheer scale and because its magnetic field is genuinely anomalous. The moon that nobody talks about is Callisto. Callisto is the outermost of the four large Galilean moons, the moons Galileo Galilei observed through his telescope in 1610 and recognized as bodies orbiting Jupiter, overturning the Ptolemaic picture of a universe centered on Earth. These four moons, Io, Europa, Ganymede and Callisto, are large enough to be considered planets if they orbited the Sun rather than Jupiter. Each is a world. Each is more than a moon in any meaningful sense. And Callisto, by the standard narrative of planetary science, is the boring one. The narrative goes like this. Callisto is ancient. Its surface is the most heavily cratered of any object in the solar system, blanketed by impact craters accumulated over 4 billion years, an undisturbed fossil record of the bombardment that shaped the early solar system. Unlike Io, which is constantly resurfaced by volcanic activity, unlike Europa, whose ice shell is cracked and rotated by tidal forces, unlike Ganymede, which shows evidence of past tectonic activity, Callisto's surface appears to have been essentially unchanged since the late heavy bombardment 3.8 billion years ago. This makes Callisto scientifically valuable as a record of the past, but it makes it seem, in the popular imagination, dead, inert, a world that sat still while everything around it evolved, a geological museum rather than an active world. But Callisto is stranger than this narrative suggests. Tonight we are going to examine what we actually know about Callisto. Not what the standard textbook summary says, but what the actual spacecraft data shows, what the anomalies are, what does not fit neatly into the picture of a dead ice and rock world parked at the edge of the Jovian system. Because Callisto has a magnetic signature that suggests something conducting beneath its surface, because Callisto has complex organic molecules on its surface that are not fully explained, because Callisto's interior structure is not what it should be if the moon formed and evolved the way our models say it should have, because Callisto sits in a radiation environment significantly different from Europa and Ganymede, and this difference may make it one of the most interesting places in the outer solar system for thinking about chemistry and possibly about the conditions for life. None of this means Callisto is about to be proclaimed the most likely home for extraterrestrial life. The point is more subtle. The point is that Callisto is genuinely strange, in ways that the standard dismissal of it as the boring Galilean moon conceals. And following its strangeness carefully reveals something about what we know and do not know about the outer solar system. If you are here because the night is long and you need something to settle into, stay. Callisto is one of those subjects where the more carefully you look, the more the initial, simple picture dissolves into something more interesting and more uncertain. Let us start with where Callisto sits and what this position means physically. The 4 Galilean moons orbit Jupiter at different distances. Io is closest, orbiting at approximately 421,700 kilometers from Jupiter's center. Close enough that Jupiter's powerful tidal forces flex and squeeze Io continuously, generating the enormous heat that drives its volcanism. Europa orbits at approximately 670,900 kilometers. Ganymede at approximately 1,070,400 kilometers. Callisto at approximately 1,882,700 kilometers, more than 4 times as far from Jupiter as Io. This distance has profound physical consequences. Jupiter has the strongest magnetic field of any planet in the solar system. Its magnetosphere, the region of space dominated by its magnetic field, extends millions of kilometers in every direction. The inner Galilean moons sit deeply embedded in this magnetosphere, subjected to intense bombardment by high-energy, charged particles trapped in Jupiter's radiation belts. Io's surface is continuously bombarded by electrons and ions that contribute to chemical transformation and atmospheric erosion. Europa's surface receives a radiation dose of approximately 5,400 millisieverts per day on its trailing hemisphere, enough to cause acute radiation sickness in a human in a matter of days. Callisto, at its greater distance, receives a significantly lower radiation dose, approximately 0.01 millisieverts per day on its surface, a factor of roughly 540,000 lower than Europa. This makes Callisto's surface, from a radiation standpoint, one of the more benign environments in the outer solar system. For potential human missions to the Jovian system, something that has been studied in advanced mission planning documents at NASA and ESA, this makes Callisto uniquely interesting. A crewed base on Callisto would be largely outside the intense radiation belts that make the inner Galilean moons extremely hazardous for electronics and people. Callisto has been identified as a potentially viable staging point for human exploration of the Jovian system, precisely because its radiation environment is manageable by near-future shielding standards. But the radiation environment has implications for chemistry as well. The intense radiation bombardment of Europa's surface drives a complex chemistry, splitting water molecules, creating peroxides and oxygen, producing sulfur compounds from Io's volcanic material that rains onto Europa. This radiation-driven chemistry is part of why Europa's surface and potentially its subsurface ocean are considered interesting for astrobiology. The radiation creates reactive compounds that could provide energy sources for life. Callisto's lower radiation environment means a different chemistry. Its surface is not being bombarded with the same intensity. The chemical processing of its surface is different. This is not necessarily worse from an astrobiological standpoint. It is different, and the implications are not fully understood. Let us now talk about Callisto's surface in detail, about what we actually see when we look at it, and why it is more interesting than the simple description of a heavily cratered, dead world suggests. The most striking feature of Callisto's surface is the ancient impact record. The surface is saturated with craters, so many craters that adding one more can only erase or overlap existing craters. This saturation represents approximately 4 billion years of bombardment without significant geological resurfacing. It is a record of the late heavy bombardment, the period approximately 3.8 billion years ago when the inner solar system was heavily bombarded by leftover planetesimals, preserved on Callisto's frozen surface. This saturation of craters is scientifically valuable precisely because it is rare. Most geologically active bodies in the solar system, Earth, Io, Europa, Titan, have surfaces that have been substantially modified since the early bombardment period. Studying the crater record on those worlds requires inference and partial evidence. Callisto presents the record nearly intact, a fossil landscape of the early solar system. But the surface is not simply a uniform cratered plain. There are several distinctive features. The most dramatic are the multi-ring structures, large impact basins surrounded by concentric rings of ridges and scarps extending hundreds of kilometers from the central impact point. The largest of these, Valhalla, is the largest impact basin in the solar system. Its central bright region is approximately 360 kilometers across. The concentric rings extend to approximately 1,900 kilometers from the center. Valhalla formed when an enormous impactor struck Callisto early in its history, sending concentric waves through the ice that then froze into the ring pattern visible today. A second large multi-ring structure, Asgard, is similar in structure, though smaller, approximately 1,400 kilometers across, including its ring system. These multi-ring basins provide information about the interior structure of Callisto at the time of impact. The way the rings formed, and specifically the fact that they formed as frozen waves rather than as conventional basin walls, indicates that the material beneath the crust at the time of impact was able to flow. This suggests either a liquid layer or a warm, ductile ice layer beneath the surface at the time these impacts occurred billions of years ago. But the most scientifically puzzling aspect of Callisto's surface is not the craters, it is what is between the craters and what the craters reveal. Callisto's surface shows evidence of a process called sublimation erosion. In this process, ice in the surface layer gradually sublimates, converts directly from solid to gas, in response to the limited solar energy reaching the outer solar system. As ice sublimates, it leaves behind darker, non-ice material, complex organic compounds and rocky material that have been mixed into the ice. Over billions of years, this sublimation erosion has concentrated the non-ice material and produced a distinctive darkening of the terrain. The dark material coating Callisto's surface contains complex organic molecules, carbon-rich compounds, including what spectroscopic analysis suggests are polycyclic aromatic hydrocarbons, carbonates, and possibly amino acid precursors. These are not simple organic compounds. They are complex molecules that represent chemical processing of the original material over long timescales. Where did these complex organics come from? The answer is not entirely clear. They may be primordial material from the original carbonaceous material that accreted to form Callisto during solar system formation. They may partly be delivered by ongoing impacts from comets and carbonaceous asteroids. They may be processed by cosmic rays and solar ultraviolet radiation over billions of years. Whatever their origin, the presence of complex organic molecules on Callisto's surface is not trivial. It represents a reservoir of chemical complexity sitting in the outer solar system. Let us now talk about the most scientifically significant anomaly about Callisto, the magnetic field interaction that first suggested something unexpected beneath its surface, and what the data from the Galileo spacecraft actually shows. When the Galileo spacecraft made 6 flybys of Callisto between 1996 and 2001, its magnetometer instrument detected something that the scientific team initially found puzzling. Jupiter generates an enormous and complex magnetic field. As Galileo flew past Callisto, it measured perturbations in Jupiter's field, distortions in the expected shape and strength of the magnetic field near Callisto. These perturbations matched a specific pattern. They were consistent with Callisto having an induced magnetic field, a magnetic field generated inside Callisto in response to the changing component of Jupiter's field that passes through the Moon. An induced magnetic field requires an electrically conducting layer inside the Moon. As Jupiter's magnetic field, which is tilted relative to Jupiter's rotation axis, sweeps past Callisto with Jupiter's rotation, the changing magnetic flux through Callisto induces currents in any conducting layer, and those currents generate their own magnetic field that partially cancels the inducing field. What can serve as this conducting layer? The most natural candidate is liquid water. A global layer of salty liquid water inside Callisto would be conducting enough to generate the induced field that Galileo detected. The same induced magnetic field signature was detected at Europa and Ganymede and was interpreted as evidence for subsurface oceans in those moons, a conclusion that has been broadly confirmed by subsequent observations. The same logic applied to Callisto suggests a subsurface liquid water ocean inside Callisto. But here is the problem. Callisto should not have a subsurface ocean. Europa has a subsurface ocean because tidal heating from Jupiter maintains liquid water beneath its ice shell. Europa is in an orbital resonance with Io and Ganymede, a configuration where the gravitational interactions among the moons continuously pump energy into them, causing tidal flexing that generates internal heat. This tidal heat is what keeps Europa's ocean liquid despite the enormous distance from the Sun. Callisto is not in the orbital resonance that drives tidal heating of the inner Galilean moons. It orbits independently, outside the resonance. The amount of tidal heating Callisto receives is estimated to be extremely small, insufficient by itself to maintain a global liquid water layer. So what keeps Callisto's ocean liquid, if it exists? The best current hypothesis involves ammonia. If Callisto's interior contains ammonia, which is a common volatile in the outer solar system, the mixture of water and ammonia has a freezing point significantly below that of pure water. A water-ammonia mixture can remain liquid at temperatures well below 0 degrees Celsius, reducing the amount of internal heat needed to maintain a liquid layer. Callisto does have enough radioactive material in its rocky component to generate some internal heat through radioactive decay. The specific calculation of whether this heat, plus any tidal contribution, is sufficient to maintain a liquid water-ammonia layer depends on the exact concentration of ammonia and the thermal properties of the ice, parameters that are not well constrained. The conclusion is uncertain but notable. The induced magnetic field that Galileo detected is most naturally explained by a conducting subsurface layer. The most plausible conducting layer is liquid water, possibly with ammonia. But the heat source that would maintain this liquid layer is unclear. Callisto may have a subsurface ocean whose existence is poorly explained by current models. Let us now talk about Callisto's interior structure, about what the Galileo flyby data tells us, and about the anomaly in that structure that is inconsistent with standard models of planetary formation. When a spacecraft flies past a moon, the gravitational pull of the moon on the spacecraft can be precisely measured from the tiny changes in the spacecraft's velocity, changes detected through the Doppler shift of the spacecraft's radio transmissions. The precise pattern of gravitational pull as the spacecraft flies past reveals the distribution of mass inside the Moon, how dense different layers are, and how differentiated the interior is. The 4 Galilean moons are expected to have formed from a similar mixture of rocky silicate material and icy material, roughly half and half by mass in the outer solar system. Under the gravity of a large body like these moons, this mixed material should differentiate, the denser rocky material sinking toward the center and the lighter icy material floating to the surface. This process is called differentiation, and it is how Earth and the other terrestrial planets became layered with dense iron cores and lighter silicate mantles. The inner Galilean moons show this differentiation clearly. Io is essentially rocky, with no significant ice. The tidal heating has driven off volatile material and differentiated the interior. Europa has a rocky interior surrounded by a water ice shell, clearly differentiated. Ganymede has a metallic iron core, a rocky mantle, and an icy outer layer, fully differentiated. Callisto should be differentiated too. With a radius of approximately 2,410 kilometers, nearly the size of Mercury, and a formation in the early solar system, Callisto has had billions of years for gravity to separate its rocky and icy components. But the Galileo gravity data says it is not, or at least not fully. The moment of inertia factor, a number derived from the gravity measurements that describes how mass is distributed inside the Moon, comes out to approximately 0.358 for Callisto. A fully differentiated body with a dense core would have a lower moment of inertia factor, mass concentrated at the center. A completely uniform body with density the same throughout would have a factor of 0.4. Callisto's value of 0.358 indicates partial differentiation, some concentration of mass toward the center, but not the complete separation of rock and ice that should have occurred. This is unexpected and unexplained. Why would Callisto be only partially differentiated? One hypothesis is that Callisto formed slowly enough that the heat generated during accretion was radiated away rather than accumulating to melt the interior. When bodies accrete, when material falls together under gravity to form a moon or planet, the kinetic energy of the infalling material converts to heat. If this heat accumulates faster than it can be radiated away, the interior melts and differentiation occurs. If the accretion is slow enough, the heat is lost and the body never fully melts. Callisto's location in the outer reaches of the Jovian accretion disk and the timing of its formation might have allowed it to accrete slowly enough to avoid full differentiation. Models suggest that Callisto could have taken significantly longer to form than the inner Galilean moons, perhaps 100 times longer, with accretion rates slow enough to prevent runaway heating and melting. But the same models predict that if Callisto is undifferentiated, its deep interior should be a roughly uniform mixture of rock and ice. A uniform interior should not have a subsurface ocean of liquid water, because there is no concentration of heat-producing radioactive elements in a central rocky core to maintain it. This creates a tension. The magnetic data suggests a subsurface ocean. The gravity data suggests an undifferentiated interior. Models struggle to explain both observations simultaneously. One possibility, and this is active research, not settled science, is that Callisto is partially differentiated in a way that the simple moment of inertia measurement cannot fully resolve. Perhaps there is a concentration of rock toward the center that is insufficient to dramatically change the moment of inertia, but is sufficient to concentrate heat-producing elements enough to help maintain a liquid layer. The interior of Callisto may be more complex than either the fully differentiated or fully undifferentiated end members. Or the induced magnetic field might have a different explanation. Though alternatives, such as conducting material in the regolith, are generally considered less likely than a liquid layer, the situation is that Callisto presents two anomalous observations: a magnetic induction signal suggesting a conducting subsurface layer, and a moment of inertia suggesting an undifferentiated interior, that are each explained by different models, and those models are not easily reconciled. Callisto is a world with a genuinely uncertain interior that does not fit neatly into our standard picture of how Galilean moons should be structured. Let us now talk about Callisto's thin atmosphere, which is another feature not usually discussed in brief descriptions of the Moon, and which adds another layer of complexity. Callisto has an atmosphere. It is extremely thin, approximately 4 billionths of Earth's sea level pressure, but it is real. It was detected by the Galileo spacecraft, and it is composed primarily of carbon dioxide. The source of this carbon dioxide atmosphere is sublimation, the same process that produces the dark, organic-rich lag deposits on the surface. Carbon dioxide ice sublimates from Callisto's surface, or carbon dioxide is released from carbonates and organic material by energetic particle bombardment, and the molecules form a tenuous gas layer around the Moon. Callisto's gravity is sufficient to retain this carbon dioxide atmosphere against thermal escape, at least partially. The atmospheric pressure is extremely low, nothing that any human could survive without a pressure suit. But the existence of a CO2 atmosphere is notable because CO2 is a key molecule in carbon chemistry, and its presence suggests that Callisto's surface is releasing chemically interesting material. Interestingly, oxygen has also been detected in Callisto's atmosphere, another molecule released by particle bombardment of the ice surface. The oxygen abundance is low, but measurable. Its presence reflects the ongoing chemical processing of the surface by the particle environment. There may also be molecular hydrogen in the atmosphere, released by the radiolysis of water ice by energetic particles, though this is more difficult to confirm. The thin atmosphere of Callisto is not thick enough to significantly moderate the surface environment. Temperatures on Callisto's surface range from approximately -108 degrees Celsius on the sunlit side to -193 degrees Celsius in the coldest shadowed regions. The atmosphere provides negligible insulation, but the existence of an atmosphere, even an extremely thin one, indicates that Callisto is not a completely inert dead world. Its surface is actively releasing material into space. Chemistry is occurring. The surface is being processed by particle bombardment and sublimation. There is a dynamic, if extremely slow, exchange between the surface, the atmosphere, and the space environment. Let us now talk about the thin exosphere and what it tells us about the surface chemistry in more detail. When energetic ions from Jupiter's magnetosphere strike Callisto's icy surface, even at the lower rates compared to the inner moons, they break apart water molecules into hydrogen and oxygen. The hydrogen, being light, can escape Callisto's gravity and is lost to space. The oxygen, being heavier, has a longer residence time and contributes to the tenuous oxygen component of the atmosphere. But more interesting is what happens to the carbon-containing compounds on the surface. Energetic particle bombardment of complex organic molecules can break them apart, rearrange them, and produce new species. This radiolytic chemistry, chemistry driven by ionizing radiation, is thought to be an important process on icy bodies in the outer solar system. On Europa, where the radiation flux is much more intense, this radiolytic chemistry is particularly vigorous, producing sulfur compounds, peroxides, and other reactive species that may eventually be transported into the subsurface ocean through ice shell dynamics. On Callisto, the radiation flux is lower, so the radiolytic chemistry is slower, but it has been operating for billions of years, and the cumulative effect on the organic inventory of Callisto's surface is not negligible. The dark organic material that coats Callisto's surface has been irradiated for the entire history of the solar system. It has been modified by whatever level of particle bombardment Callisto receives, even at its greater distance from Jupiter. The result is a complex organic chemistry that is incompletely characterized. This matters for thinking about Callisto as a potential astrobiological site. Not because Callisto's surface is a promising environment for life, which it clearly is not, given the temperature, pressure, and radiation conditions, but because the complex organic chemistry on the surface may be relevant to the chemistry of any subsurface ocean. If material cycles between the surface and subsurface, through impacts, through resurfacing processes, through gradual incorporation of surface material, then the rich organic chemistry of the surface might provide organic precursors to any liquid water layer beneath. This is speculative. The exchange between Callisto's surface and any subsurface ocean is not well constrained. The ice shell of Callisto, if it has a subsurface ocean, is thought to be thick, possibly hundreds of kilometers, which would significantly limit the exchange of surface material with the ocean. But speculative is not the same as unreasonable. The question of what organic chemistry is occurring in and around Callisto is a legitimate scientific question with uncertain answers. Let us now talk about how Callisto compares specifically to Europa, the moon it is most often overshadowed by, and what this comparison reveals about the different ways a moon can be scientifically interesting. Europa has become the poster child for the search for life in the outer solar system. The reasons are compelling. Europa's subsurface ocean is well established. The induced magnetic field, the surface features showing evidence of ice shell dynamics, the tidal heating that maintains the ocean. The ocean is in contact with a rocky sea floor, unlike Callisto, where any ocean would be sandwiched between layers of ice if the interior is poorly differentiated. This rock-water interface is important because it allows for hydrothermal circulation. Warm water rising through cracks in the sea floor, leaching minerals and potentially creating the chemical gradients that could support chemotrophic life. Europa's ocean has been maintained for billions of years by tidal heating. Its chemistry is actively driven by the radiolytic compounds produced at the surface and potentially transported into the ocean. Callisto's putative ocean is less well established, sits in a body with an uncertain thermal history, and, if it exists, sits between ice layers without a clear rock-water interface. It is, in many respects, a less compelling astrobiological target than Europa. But there are reasons why Callisto deserves attention alongside Europa, rather than being simply dismissed as the inferior option. First, the radiation environment. Any mission to Europa must contend with one of the most intense radiation environments in the solar system outside the Sun itself. Electronics must be heavily shielded. Orbit insertion requires careful trajectory design to minimize radiation exposure. Any long-duration orbiter faces cumulative radiation damage that limits mission lifetime. The Europa Clipper mission, scheduled to arrive at the Jovian system in 2030, is designed for repeated flybys rather than a sustained orbit around Europa, specifically because the radiation environment at Europa orbit would damage the spacecraft too quickly. At Callisto, these radiation concerns essentially disappear. A spacecraft in orbit around Callisto experiences a radiation dose orders of magnitude lower than one at Europa. This makes sustained orbital science much more feasible and much less demanding on spacecraft design. Second, surface accessibility. If we want to land on one of the Galilean moons, Callisto's surface is far more accessible than Europa's. Europa's surface is relatively young, a few tens of millions of years old at most, and shows complex tectonic features, fractures, and disrupted terrain. Callisto's surface is ancient and, while heavily cratered, is topographically more predictable. An ancient, heavily cratered surface is actually easier to model for landing purposes than a dynamically active young surface with complex features. Third, organic chemistry. The complex organics on Callisto's surface have no clear equivalent on Europa, where the intense radiation continuously processes the surface chemistry towards simpler and more oxidized species. Callisto's surface organic chemistry, accumulated over billions of years at lower radiation levels, may represent a different and potentially more complex organic inventory. Fourth, the mystery of the partially differentiated interior. Callisto's anomalous interior structure means that it represents a different type of object from the inner Galilean moons, a body that either formed differently or evolved differently and retains a record of that different history. Understanding why Callisto is partially differentiated when it should be fully differentiated would tell us something important about the conditions in the early Jovian accretion disk. Let us now talk about what the Galileo spacecraft actually revealed about Callisto's surface at high resolution. Because the Voyager flybys in 1979 gave us global views, but Galileo's close approaches in the 1990s revealed detail that changed the picture. The Voyager images of Callisto showed a heavily cratered world, with the large multi-ring structures Valhalla and Asgard clearly visible. The general impression was of a uniformly dark, heavily pockmarked surface, geologically dead. Galileo's high-resolution images, taken during its 6 Callisto flybys, revealed a more complex surface. The craters themselves showed internal structure, bright icy peaks and walls surrounded by dark floors where ice had sublimated and left behind the dark organic lag deposit. The rims of craters showed bright, fresh ice exposed by the impact. The floors showed the dark processed material. More striking was the terrain between craters. At high resolution, Callisto's surface shows a distinctive texture, a landscape of dark, irregular knobs and hills, separated by bright, icy patches. This texture is the result of sublimation erosion operating over billions of years. Ice has sublimated from the elevated terrain, concentrating the dark material into the knobby texture, while fresh ice is exposed in the lower areas. Some regions show concentrations of unusually bright material, ice-rich patches that have been less processed by sublimation erosion. Other regions show concentrations of unusually dark material, areas where the organic-rich lag deposit is particularly thick. The Galileo images also revealed that some of Callisto's craters have been modified in unexpected ways. Some craters show central pits rather than peaks, a morphology associated with impacts into targets with volatile-rich layers near the surface. The presence of volatiles causes the crater to collapse differently during formation, producing the distinctive pit morphology. This observation is consistent with Callisto having a volatile, rich, ice-rich subsurface, even if the very outermost surface is dominated by the dark, organic lag deposit. One of the most surprising observations from Galileo was evidence of a process called viscous relaxation in some of the older craters. Viscous relaxation occurs when the material of a crater floor slowly flows over geological time, flattening the originally steep crater walls and removing topographic relief. On icy worlds, at the temperatures typical of the outer solar system, water ice is sufficiently ductile over millions to billions of years to flow and relax crater topography. The observation of viscous relaxation in some Callisto craters, particularly older, larger craters, suggests that at some point in Callisto's past, the ice was warm enough to flow. This is additional evidence for a geologically warmer past, perhaps associated with the early period when radioactive decay was generating more heat in the rocky component, that is consistent with the undifferentiated or partially differentiated interior. Let us now talk about the specific observations of Callisto's atmosphere made by Galileo and what they revealed. The Galileo spacecraft carried an ultraviolet spectrograph that detected absorption features in sunlight reflected from Callisto's surface and the exosphere above it. These absorption features identified carbon dioxide as a component of the thin atmosphere. The carbon dioxide was found to be non-uniformly distributed. Concentrations were higher in some regions than others, particularly in areas that receive more sunlight, consistent with thermal sublimation releasing CO2 from the surface. The day-night distribution of CO2 was consistent with a diurnal cycle, more CO2 subliming during the local day and the molecules migrating and partially refreezing at night. The Galileo plasma wave experiment detected electron density enhancements in Callisto's ionosphere during flybys. This indicates that the thin CO2 atmosphere is being partially ionized by solar ultraviolet radiation and by energetic particle bombardment, producing a thin ionosphere above the neutral atmosphere. These atmospheric observations confirm that Callisto is not completely inert. There is a surface-atmosphere exchange cycle. There is photochemistry occurring in the thin gas layer. There is interaction between the atmosphere and the energetic particle environment from Jupiter's magnetosphere, even at Callisto's distance. The detailed chemistry of Callisto's atmosphere is not fully characterized. The Galileo instruments detected CO2 and oxygen, but had limited sensitivity to other species. Whether other volatile compounds, methane, nitrogen compounds, sulfur compounds, are present in the atmosphere at low concentrations is unknown. Future missions with more capable spectrographic instruments would be able to characterize Callisto's atmospheric chemistry in much greater detail. The composition of the atmosphere provides a window into the volatile chemistry of the surface, which in turn reflects the history of material delivery to Callisto and the processing that material has undergone over billions of years. Let us now talk about what future missions to the Jovian system could reveal about Callisto, and what makes Callisto a scientifically compelling stop even for missions primarily focused on Europa or Ganymede. The Europa Clipper mission, launched by NASA in October 2024 and scheduled to arrive at the Jovian system in 2030, is focused on Europa. But its trajectory through the Jovian system will bring it past Callisto. Whether Clipper will conduct detailed Callisto observations depends on mission planning priorities. Primarily, its instruments are designed and calibrated for Europa science, but opportunistic Callisto observations are possible. The JUICE mission, Jupiter Icy Moons Explorer, launched by the European Space Agency in April 2023 and scheduled to arrive at the Jovian system in 2031, is specifically designed to investigate Ganymede as its primary target. But its mission plan includes flybys of all 4 Galilean moons, including Callisto. JUICE will conduct 21 flybys of Callisto before ultimately entering Ganymede orbit in 2034. These flybys are planned to characterize Callisto's surface, atmosphere, interior, and magnetic environment in significantly greater detail than Galileo was able to provide. The JUICE Callisto flyby science is designed to address several key questions. Is there a subsurface conducting layer consistent with the Galileo magnetic induction signature? If so, how deep is it, and what are its properties? What is the detailed composition of the surface organic material? What is the structure of the thin atmosphere? How has Callisto's interior evolved? Why is it apparently undifferentiated? These are genuine open scientific questions that JUICE is positioned to address. The results, when they come in the mid-2030s, will either confirm or modify our current picture of Callisto in significant ways. If JUICE confirms the magnetic induction signature with better characterization, particularly if it can constrain the depth and electrical conductivity of the conducting layer, it will provide much stronger evidence for a subsurface ocean. If it finds that the conducting layer is near the surface rather than deep, it might suggest a different interpretation, perhaps a layer of conducting impurities in the ice, rather than a liquid water ocean. The detailed surface composition measurements from JUICE's spectrographic instruments will characterize the organic material in far greater detail than was possible with Galileo. Whether the organics include amino acid precursors, whether they show signs of aqueous alteration that would indicate contact with liquid water at some point in their history, whether they contain nitrogen compounds. These are questions that better spectroscopy could address. And the interior structure measurements from the gravity field mapping during multiple flybys will improve the determination of the moment of inertia and potentially reveal more detail about whether Callisto is truly undifferentiated or has a more complex interior than the simple uniform mixing picture suggests. Callisto, the forgotten moon, the boring Galilean, is about to receive its most detailed scientific examination since Galileo. The results of JUICE's 21 flybys will likely change our understanding of this world in ways that are difficult to predict specifically, but that will certainly add to the picture of strangeness that the existing data already suggests. Let us now talk about the broader significance of Callisto for understanding the outer solar system, about what Callisto represents in the larger context of icy moon science, and what it tells us about the variety of worlds that exist beyond the asteroid belt. The outer solar system is full of icy moons. Jupiter has 95 known moons. Saturn has 145 or more. Uranus has 27. Neptune has 16. Many of these are small, irregular bodies, captured asteroids or Kuiper belt objects. But many are large, differentiated or partially differentiated worlds with complex geologies, internal oceans, thin atmospheres, and surface chemistry ranging from water ice to ammonia to methane to nitrogen to exotic organics. Callisto represents a specific type in this diversity, a large icy moon that formed in the outer regions of a giant planet's accretion disk, accreted slowly enough to avoid full differentiation, and has preserved its early chemical character while accumulating a fossil record of the early solar system's bombardment. It is a type specimen of the slowly accreted, partially differentiated icy moon. Understanding Callisto tells us something about formation conditions in giant planet accretion disks. The fact that Callisto is undifferentiated while Ganymede, similar in size and composition, is fully differentiated, suggests that something was different about their formation environments or timescales. Pinning down what that difference was requires better characterization of Callisto's interior, the kind of characterization that JUICE can provide. Callisto's ancient surface is also a unique archive. If we want to understand what the early solar system was like, what the bombardment record looked like, what the composition of impactors was, what the volatile inventory of the early outer solar system was, Callisto's surface preserves this record more completely than almost any other large body we can access. Reading that record with better instruments would be like reading a 4-billion-year-old diary of the solar system's early history. And Callisto's possible subsurface ocean, uncertain, poorly understood, apparently maintained without a clear heat source, adds it to the growing list of outer solar system bodies that may harbour liquid water beneath their surfaces. Europa, Ganymede, Enceladus, Titan, possibly Pluto, possibly Ceres. The outer solar system appears to be far more hydrologically active than early models predicted, and Callisto's possible ocean is another data point in that increasingly complex picture. The outer solar system is not a collection of frozen inert balls. It is a diverse set of worlds with internal oceans, active geology, complex surface chemistry, thin atmospheres, and histories that we are only beginning to understand in detail. Callisto, the forgotten moon, the boring one, is stranger than the standard dismissal suggests. It has a surface that is a fossil record of the early solar system, an interior that refuses to differentiate the way models say it should. A magnetic signature suggesting a subsurface ocean without a clear heat source to maintain it. A thin atmosphere releasing complex organic chemistry into space. A radiation environment that makes it paradoxically more accessible for future human or robotic exploration than its more dramatic neighbours. Callisto is not boring. Callisto is one of the most scientifically interesting objects in the solar system precisely because it defies simple categorization. It sits at the outermost edge of the Galilean system, quiet, ancient, dark, and strange, accumulating craters and organic chemistry and a magnetic mystery for 4 billion years while the inner moons were resurfaced and heated and dynamically active. It waited. And we are only now beginning to ask it the right questions. Let us talk about something that requires a specific kind of attention, about what the cratered surface of Callisto actually preserves, and why planetary scientists treat it as one of the most valuable geological archives in the solar system. The concept of crater saturation is easy to state and harder to fully grasp. When a surface is said to be saturated with craters, it does not simply mean heavily cratered. It means the surface has reached a statistical equilibrium where adding new craters destroys old ones at the same rate. The surface cannot record more craters because every new impact erases evidence of previous impacts. Callisto's surface has reached this saturation in its oldest regions. The implication is extraordinary. Every square kilometre of ancient terrain on Callisto has been struck so many times that the original surface, whatever it looked like when Callisto first formed, is completely obliterated. What we see is not the beginning, but the end point of a long statistical process of bombardment. But the saturation density itself is informative. The specific size-frequency distribution of craters on Callisto, how many craters of each size exist per unit area, tells us something about the population of impactors that struck it. The size distribution of craters reflects the size distribution of impactors, and that size distribution tells us about the population of planetesimals in the early outer solar system. Comparing the crater size-frequency distribution on Callisto to those on other heavily cratered surfaces, the lunar highlands, the old terrain on Mars, reveals both similarities and differences. The similarities suggest some commonality in impactor populations across the solar system. The differences may reflect the different orbital dynamics of impactors in the outer solar system versus the inner solar system. This is planetary science using Callisto as a measurement instrument, not exploring it as a destination, but reading it as a record. The large impact basins, Valhalla, Asgard, and several smaller examples, are particularly informative. The morphology of an impact basin encodes information about the target at the time of impact. A basin forming in warm, ductile ice looks different from one forming in cold, brittle ice. The multi-ring structure of Valhalla suggests that the target at the time of impact was partially liquid, or at least warm enough to flow. The impact energy sent waves through the viscous material that froze into the ring pattern. When did the Valhalla impact occur? The density of smaller craters on top of the Valhalla ring system gives an estimate. More smaller craters on top means more time for smaller impactors to arrive after the big one. The crater density suggests Valhalla formed early in Callisto's history, possibly during or shortly after the late heavy bombardment, when the impactor flux was higher. If Callisto's interior was warm enough at the time of Valhalla's formation to allow the multi-ring morphology, this is consistent with internal heat from radioactive decay being significant in the early history. Consistent with the hypothesis that Callisto was warmer early on, when its radioactive elements were fresher and generating more heat, and has cooled progressively since. The oldest craters on Callisto have flat floors and degraded walls, evidence of viscous relaxation over billions of years. Younger craters are sharper, more pristine. The progression from degraded old craters to fresh young craters gives a temporal sequence that parallels the cooling of the interior. Callisto's surface is a time machine in a specific and literal sense. Reading the morphology of its craters in order of their formation age gives us a history of how the interior temperature has evolved. From warm enough to allow viscous relaxation to cold enough to preserve sharp crater morphology. Let us now talk about the specific and somewhat counterintuitive reason why Callisto's ancient, geologically inactive surface makes it a better candidate for certain kinds of exploration than the more geologically active inner moons. Consider the problem of landing on an icy moon. You want to put a spacecraft gently on the surface, perhaps a lander or rover that operates for months or years. To do this successfully, you need to predict what the surface is like, how rough it is, whether it is stable, what the regolith properties are. On Europa, the surface has been geologically active in the recent past, possibly within the last tens of millions of years. The terrain is complex, showing ridges, bands, chaos regions where the surface appears to have been disrupted and refrozen. The composition of the surface varies significantly across short distances. Some regions are covered in salt deposits or sulfur compounds from Io's volcanic plumes. The surface is constantly being modified by the intense radiation, which drives chemical reactions and may cause physical changes in the ice structure. Landing on Europa requires dealing with this complexity. You cannot assume that what you see from orbit at relatively low resolution represents what you will find at the 10-centimeter scale relevant to landing. The terrain is unpredictable at fine scales. On Callisto, the situation is different. The surface has been stable for billions of years. The processes shaping it, crater formation, sublimation erosion, gradual accumulation of dark material, operate on timescales of millions to billions of years. They are predictable and uniform. The regolith, the loose surface material, has had billions of years to develop and equilibrate. Its properties, while not perfectly characterized, are more stable and predictable than Europa's actively processed surface. The dark, organic-rich lag deposit that coats Callisto's surface produces a relatively uniform dark layer. Beneath this, ice-rich material. The texture is knobby, the sublimation erosion knobs, but at scales relevant to landing, the surface is more uniform than Europa's. For a lander mission, Callisto offers something Europa does not: geological stability and surface predictability. The same ancient surface that makes Callisto seem boring from the perspective of recent geological activity makes it more accessible as a landing site. This has been recognized in mission planning documents. A Callisto lander, if funded and designed, would face significantly fewer engineering challenges in terms of terrain uncertainty than a Europa lander. The radiation environment at the surface is also far more benign, extending the operational lifetime of electronics and reducing the shielding requirements. A long-duration Callisto surface mission, something like the Curiosity or Perseverance rover concept applied to an outer solar system moon, is technically more feasible at Callisto than at any other Galilean moon. What would such a mission find? It would characterize the dark organic material in detail, identifying specific compounds, measuring their abundance and distribution, searching for signs of aqueous alteration that would indicate contact with liquid water at some point. It would measure the subsurface structure, whether there is a more ice-rich layer beneath the organic lag, at what depth, and what its properties are. It would characterize the thin atmosphere locally, measuring CO2 concentration and its variation through the day, searching for other volatile species. It would place seismometers to listen for internal activity. Even at Callisto's level of quiescence, low-level tidal deformation from Jupiter might produce detectable seismic signals that constrain the interior structure. Such a mission would extract extraordinary scientific value from an object that planetary science has largely overlooked. Let us now talk about Callisto's relationship to the broader inventory of icy bodies in the outer solar system, about what it shares with other bodies and what makes it distinctive. Pluto, recently reclassified as a dwarf planet, but still one of the most scientifically interesting bodies in the outer solar system, presents an interesting comparison. Like Callisto, Pluto is a large icy body in the outer solar system. Like Callisto, Pluto has complex organic material on its surface, the dark reddish material called tholin that coats much of Pluto's surface and is produced by cosmic ray processing of organic molecules over billions of years. Like Callisto, Pluto was long considered a boring, inert world, before New Horizons revealed nitrogen ice plains, mountain ranges of water ice, evidence of geological activity, and a surprisingly thin but real atmosphere. Callisto's dark organic material is compositionally similar to tholin in some ways. Both are complex carbonaceous compounds produced by long-term radiation processing. The difference is that Pluto's tholins form from nitrogen-rich organics, including nitrogen ice, while Callisto's dark material appears to come from carbonaceous material delivered by impactors or already present in the original accreting material. The comparison with Pluto is instructive because it illustrates how systematically wrong we can be about what a world is like based on distant observations. Before New Horizons, Pluto was considered essentially dead, a frozen rock-ice body with no significant geological activity. New Horizons revealed a geologically complex world with active sublimation, glacial flow, possible cryovolcanism, and a history that is still being unravelled. We have only Voyager 2 data and Galileo flyby data for Callisto. Our knowledge of Callisto today is roughly comparable to our knowledge of Pluto before New Horizons. We know the large-scale features, we know the basic composition, we have some magnetic measurements that hint at interior structure, but we lack the high-resolution, complete surface mapping, detailed compositional mapping, and in-situ measurements that transform a fuzzy, distant object into a real, complex world. There is every reason to believe that Callisto, examined at the level of detail that New Horizons examined Pluto, would reveal complexity and strangeness that current data does not capture. The lesson of Pluto is that outer solar system bodies that appear simple from a distance are not. The lesson of Enceladus, the small Saturnian moon that nobody expected to have active geysers of water vapour erupting from its south pole, is that outer solar system bodies can be dramatically more active than size and position would suggest. The lesson of Titan, a moon with a dense nitrogen atmosphere, methane lakes, and a complex organic chemistry on its surface, is that the outer solar system is far more chemically rich and varied than early models predicted. Callisto has not yet had its New Horizons moment. Its surprising complexity has not yet been revealed at high resolution, but the hints are there in the existing data: the magnetic anomaly, the anomalous interior structure, the complex organic surface chemistry, the thin, real atmosphere. Let us now talk about something that is rarely emphasized in discussions of Callisto, about what the presence of complex organic material on its surface means in the broader context of organic chemistry in the solar system. The solar system contains organic material, carbon-containing compounds, in a variety of locations and forms. Comets carry organic molecules including amino acids. The Stardust mission returned cometary material from Wild 2 containing glycine, the simplest amino acid. Carbonaceous chondrite meteorites, a class of meteorite that has not been significantly heated since formation, contain amino acids, sugars, nucleobases, and other complex organics. The interstellar medium contains organic molecules, including complex species. Titan has an extraordinarily rich organic chemistry in its atmosphere and on its surface. The surfaces of the outer solar system icy bodies, including Callisto, represent another reservoir of complex organic chemistry. The organics on Callisto's surface have been accumulating and being processed for the entire age of the solar system. They were delivered by comet impacts and incorporated from the original accreting material. They have been irradiated by cosmic rays and solar ultraviolet. They have been thermally processed to whatever extent Callisto's interior heat has affected the near surface. The result is a surface whose organic chemistry has been cooking, very slowly, for 4.5 billion years. Spectroscopic observations of Callisto's surface from Earth and from Galileo have detected absorption features consistent with carbon dioxide, carbonates, and complex hydrocarbons. The dark material shows absorption features in the near-infrared that are broadly consistent with complex carbonaceous material similar to what is seen in carbonaceous meteorites. But the spectral resolution of available observations is limited. We are matching broad absorption features to categories of compound, rather than identifying specific molecules. A more detailed spectroscopic examination, particularly with instruments capable of detecting the specific molecular signatures of individual compounds, could reveal whether amino acids, nucleobases, sugars, or other prebiotic molecules are present on Callisto's surface. This is not a frivolous question. The presence of prebiotic chemistry on the surface of an outer solar system body that may have a subsurface ocean is scientifically significant. It raises the question of whether surface organics could be delivered to the ocean, and if so, what chemistry might occur at the rock-water interface or within the liquid-water layer. The inventory of organic chemistry on Callisto's surface is genuinely unknown at the level of detail required to answer these questions. Better spectroscopy from a spacecraft in close orbit around Callisto with instruments designed for this purpose could transform our understanding. Let us now talk about what is known about Callisto's formation, about the specific models that attempt to explain how it formed in the outer Jovian accretion disk, and why it ended up so different from Ganymede, despite similar sizes and bulk compositions. Both Callisto and Ganymede formed in the outer parts of the Jovian proto-satellite disk, the disk of gas and dust that surrounded Jupiter during its formation, from which the Galilean moons accreted. Both are roughly similar in size. Callisto's radius is about 2,410 kilometers, Ganymede's about 2,634 kilometers. Both have bulk compositions that imply roughly half rocky silicate material and half icy material. Yet Ganymede is fully differentiated. It has an iron core, a rocky mantle, and an icy outer layer. Callisto is partially differentiated, or possibly undifferentiated. Its interior is a heterogeneous mixture of rock and ice, with no clear separation. The leading explanation for this difference involves the rate of accretion. If Ganymede accreted quickly, building up mass rapidly from the dense inner part of the Jovian proto-satellite disk, the kinetic energy of infalling material would have accumulated faster than it could be radiated away, heating the interior to temperatures sufficient to melt and differentiate the rocky and icy components. Callisto, in this model, accreted more slowly, sitting farther out in the disk where material was less dense and the accretion rate was lower. The slower accretion allowed the heat generated to escape, keeping the interior below the melting point of ice. Without melting, there was no differentiation. Callisto simply grew by adding material without ever developing the full internal mobility that would separate rock and ice. Models by researchers including Torrance Johnson and John Lunine have explored this scenario and found it physically plausible. The factor of roughly 100 in accretion timescale between Ganymede and Callisto required by the models is within the range that differential disk density profiles could explain. But these models are not uniquely constrained. The properties of the Jovian proto-satellite disk, its density profile, temperature structure, composition, and time evolution, are not directly observable. We infer them from the current properties of the Galilean moons and from models of giant planet formation. The models that explain the Ganymede-Callisto dichotomy are plausible but not proven. An alternative possibility is that both moons initially accreted in similar conditions, but that a late event differentiated Ganymede and not Callisto. A large impact could potentially melt and differentiate a moon that had previously remained solid. Or an episode of enhanced tidal heating, perhaps associated with a different orbital configuration in the early Jovian system, could have warmed Ganymede sufficiently for differentiation. The orbital resonance configuration of the Galilean moons may itself have evolved over time. The current Laplace resonance, where Io, Europa and Ganymede are in a 4:2:1 orbital period ratio, may not always have existed in its current form. The resonance could have been established through orbital migration, and the associated tidal heating may have varied through Ganymede's history. Callisto, outside the resonance, would not have participated in these tidal heating episodes. Understanding how the Galilean moon system reached its current orbital configuration and how that evolution affected the differentiation history of each moon is an active area of theoretical research. The JUICE mission will provide new constraints on the interior structures of multiple Galilean moons, allowing better tests of these formation and evolution models. Let us now talk about Callisto's place in human exploration planning, because this is an aspect that often goes unmentioned in purely scientific discussions, but that connects the abstract science to the concrete question of where humans might eventually go. NASA's Design Reference Architecture 5.0 for Mars missions and various concept studies for outer solar system exploration have examined the Jovian system as a potential destination for human exploration in the post-Mars era. The challenges are formidable. The transit time to Jupiter, even with advanced propulsion, would be measured in years, and the radiation environment of the Jovian system presents serious risks for crew. But Callisto has a specific property that makes it stand out in these analyses. Its radiation dose rate at the surface, approximately 0.01 millisieverts per day, is low enough to be manageable with reasonable shielding. By comparison, astronauts on the International Space Station receive about 1 millisievert per day. A surface habitat on Callisto would need to provide similar or somewhat better shielding to the ISS, which is technically achievable. The surface gravity of Callisto is approximately 0.126 g, about 12.6% of Earth's. This is lower than Mars at about 38%, lower than the Moon at about 16.5%. The health implications of long-duration exposure to this level of gravity are not well understood. As discussed in other contexts, we have very limited data on partial gravity physiology. But Callisto's surface gravity is at least sufficient to orient a human in a meaningful up-down direction and to provide some mechanical loading to bones and muscles. A Callisto base would be cold, surface temperatures near -130 degrees Celsius on average. But this is manageable with insulated habitat designs. The absence of significant geological activity means the habitat site is stable. The ancient, predictable terrain means site selection is straightforward compared to active worlds. From Callisto, the rest of the Jovian system is accessible by spacecraft. Remote-operated vehicles could fly to Europa, Ganymede, and Io. Astronauts in Callisto orbit or on the surface could control these vehicles with minimal communication delay. Callisto is close enough to the other Galilean moons that round-trip communication delays would be seconds to minutes, rather than the hours involved in Earth-based control. This makes Callisto a potential hub for human exploration of the Jovian system, a radiation-safe base from which crewed and uncrewed vehicles could explore the more scientifically compelling but more radiatively hazardous inner moons. This concept has been called the Callisto Gateway in some mission concept documents, analogous to the Lunar Gateway concept for moon exploration, where an orbiting platform provides a staging point for surface missions. A Callisto surface base or orbiting station could serve a similar function for Jovian system exploration. The scientific and strategic case for Callisto in long-term outer solar system exploration is stronger than its current scientific profile might suggest. It is not just a scientifically interesting world in its own right, it is a potentially strategic location for human presence in the outer solar system. Let us now talk about something that connects Callisto to the wider question of what we know and do not know about the outer solar system, about the general phenomenon of outer solar system bodies being far stranger than initial assessments suggested. The history of outer solar system exploration is largely a history of initial dismissal followed by radical revision. Io was expected to be geologically dead before Voyager 1 arrived and revealed the most volcanically active body in the solar system. The active volcanism, hundreds of volcanoes, lava flows covering the surface continuously, plumes of sulfur and sulfur dioxide erupting into space, was entirely unanticipated. Enceladus was a small moon of Saturn expected to be geologically inert based on its size. Cassini revealed active geysers erupting from fractures in the South Polar region, a subsurface ocean confirmed by direct sampling through the plumes, and complex organic chemistry, including molecular hydrogen, indicating hydrothermal reactions on the sea floor. Enceladus is now one of the highest priority targets in the search for extraterrestrial life. Titan was known to have an atmosphere before Cassini arrived, but the extent and complexity of that atmosphere, dense nitrogen with methane rain, rivers and lakes, hydrocarbon seas at the poles, complex organic chemistry producing a permanent orange haze, exceeded even optimistic expectations. Pluto, as mentioned, was expected to be an inert frozen ball, and turned out to have active geology, nitrogen ice glaciers, complex atmospheric chemistry, and possibly cryovolcanism. Arrokoth, the Kuiper Belt contact binary visited by New Horizons in 2019, revealed that at least some planetesimals in the early solar system came together through gentle accretion rather than violent collisions, constraining models of solar system formation. Each of these discoveries required sending a spacecraft close enough to actually see the object in detail. None were predicted from Earth-based observations alone. All required the specific, high-resolution, multi-instrument examination that only a dedicated spacecraft encounter can provide. Callisto has never had such an encounter. The Voyager flybys gave broad views. The Galileo flybys gave some detail and the crucial magnetic field measurements. But Callisto has never had a spacecraft dedicated to it, has never been examined at the resolution that revealed Pluto's mountains or Enceladus's geysers or Titan's lakes. We do not know what a dedicated, high-resolution examination of Callisto would reveal. Given the track record of outer solar system exploration, the appropriate prior is that it would reveal things we did not predict. Strangeness at scales not yet examined, processes not yet detected, chemistry not yet characterized. The specific strangeness that existing data already hints at, the magnetic anomaly, the undifferentiated interior, the complex organic surface, suggests that Callisto is already surprising at the level of detail we have reached. What additional surprises await closer examination is genuinely unknown. Let us now talk about the specific timeline of when we will get the next significant data from Callisto, about what JUICE will actually do during its Callisto flybys, and what instruments will be examining what questions. JUICE, Jupiter Icy Moons Explorer, launched April 14, 2023. It is currently in transit to the Jovian system, using gravity assists from Earth and Venus. It will arrive at Jupiter in July 2031. Before entering Ganymede orbit in 2034, it will conduct flybys of Callisto, Europa, and Ganymede. The Callisto flyby sequence is the most extensive dedicated examination of Callisto ever planned. 21 flybys of Callisto, more than 3 times the 6 flybys conducted by Galileo, with closest approach distances ranging from a few hundred to a few thousand kilometers. These flybys serve multiple scientific purposes and trajectory design purposes simultaneously. The JUICE instrument payload relevant to Callisto science includes several key instruments. Janus, a camera system, will image Callisto's surface at resolutions significantly better than the best Galileo images in many areas. The Galileo camera obtained high-resolution images of relatively small patches of Callisto's surface during its flybys. JUICE's extended flyby sequence will allow more extensive high-resolution coverage, not global mapping at the highest resolution, but substantial expansion of the detailed surface coverage. MAGIS, the Moon's and Jupiter Imaging Spectrometer, will map the surface composition in detail across near-infrared wavelengths. This instrument is capable of identifying specific molecular species, distinguishing different types of ice, different organic compounds, carbonates, salts, at spatial resolutions substantially better than previous compositional mapping. The organic surface chemistry of Callisto will be characterized in far greater detail than has been possible. SWI, the sub-millimeter wave instrument, will probe the thermal structure of the atmosphere and surface, and could detect trace gas species in the thin atmosphere, including species that were below the detection threshold of Galileo instruments. 3GM, the radio and plasma wave instrument, and also the gravity science package, will measure the magnetic environment during each flyby, providing multiple measurements of the magnetic induction signature with different geometries. Multiple measurements at different orbital phases of Jupiter, when the inducing field component is different, will allow much better characterization of the conducting layer. The gravity field measurements during multiple flybys will improve the determination of the moment of inertia to constrain the interior structure. RPWI, the radio and plasma wave investigation, will measure the plasma environment around Callisto and characterize the ionosphere in detail. Together, these instruments will address the key open questions about Callisto: the subsurface conducting layer, the surface organic chemistry, the atmospheric composition, and the interior structure. The answers will not come until the mid-2030s, but they will substantially change our picture of this world. Let us now talk about something more speculative but scientifically legitimate, about the specific question of whether Callisto's putative subsurface ocean could be an environment of interest for astrobiology, even given the challenges compared to Europa. The standard astrobiological narrative about the Galilean moons places Europa at the top and Callisto somewhere near the bottom. The reasoning is that Europa's ocean has better energy sources, tidal heating maintaining the ocean, radiation-driven surface chemistry potentially delivering oxidants, and a rock-water interface that could support hydrothermal circulation. Callisto's ocean, if it exists, sits between ice layers without obvious rock-water contact, in a body with unclear heat sources, in a lower radiation environment that provides less chemical energy input. This reasoning is sound as far as it goes, but it makes assumptions that deserve examination. First, the assumption that a rock-water interface is necessary for life. Earth's hydrothermal vents, where life flourishes in the absence of sunlight, do depend on rock-water chemistry. But Earth-based hydrothermal systems are not the only models for life in liquid water environments. Life in the water column of Earth's deep ocean, far from hydrothermal vents, sustained by the slow rain of organic material from above, represents a different model. Life in subglacial lakes in Antarctica, sustained by the slow dissolution of minerals from the ice and rock interfaces, represents another. If Callisto's ocean is not in contact with rock, it might still have chemical gradients maintained by other means. The dissolution of soluble minerals from the ice, the slow settling of rocky particles that might reach the ocean from impacts that penetrate deeply enough, the delivery of material from the surface through uncharacterized processes. Second, the assumption that lower radiation input is simply worse from an astrobiological standpoint. High radiation drives chemistry, but it also destroys organic molecules that already exist. The balance between constructive and destructive effects of radiation is not straightforward. Callisto's lower radiation surface might preserve complex organics that would be destroyed in Europa's intense radiation environment. If those organics reach the ocean, they could represent an organic carbon source for potential life. Third, the uncertainty about Callisto's heat sources. We noted that the heat source for a Callisto subsurface ocean is unclear. Tidal heating is minimal, radioactive decay may or may not be sufficient. But our models of Callisto's interior are uncertain. If the interior is somewhat more differentiated than the moment of inertia suggests, with some concentration of heat-producing elements, the radioactive heat flux could be higher than nominal estimates. These considerations do not make Callisto a more compelling astrobiological target than Europa. Europa remains the priority, for good reasons, but they suggest that dismissing Callisto as astrobiologically irrelevant is premature. The question of whether Callisto's ocean, if it exists, could support any form of life or life-supporting chemistry is genuinely open. The honest answer is that we do not know enough about Callisto's interior, its ocean chemistry, or its heat sources to make a confident astrobiological assessment. The data needed to make that assessment does not yet exist. Let us now talk about what the next decade of Callisto science looks like, beyond JUICE, about what additional data could come from other missions, and how the picture of Callisto might evolve. The Europa Clipper mission, arriving at Jupiter in 2030, is focused on Europa, but its trajectory includes occasional passes of Callisto, and its instruments could potentially acquire useful Callisto data during these passes. The magnetometer on Europa Clipper could provide additional measurements of the magnetic induction at Callisto, complementing the JUICE measurements and improving the characterization of the conducting layer. Whether such observations are planned, or will be planned, depends on mission operations decisions that have not yet been finalized. The Dragonfly mission, the rotorcraft lander heading to Saturn's moon Titan, provides an indirect, relevant data point. Dragonfly will characterize Titan's complex organic chemistry at the surface in unprecedented detail. Titan's surface organics and Callisto's surface organics are both products of long-term radiation processing of organic material in the outer solar system. What Dragonfly finds about the complexity and diversity of Titan's organic chemistry will inform predictions about what a comparable examination of Callisto's organics might find. Ground-based and space-based telescopic observations continue to improve. The James Webb Space Telescope has already returned observations of Jovian system objects with significantly improved spectroscopic sensitivity compared to previous space telescopes. Webb observations of Callisto could improve the characterization of surface organics from Earth. The specific capabilities of Webb's NIR spec and MIRI instruments, sensitive to different wavelength ranges, would provide complementary compositional information. Future proposed missions include concepts for a Callisto orbiter specifically, and for landers on one or more Galilean moons. None of these are currently in development. They exist at the concept stage, awaiting a favourable decadal survey recommendation and funding. The 2023 to 2032 Planetary Science Decadal Survey did not prioritise a dedicated Callisto mission, focusing instead on Uranus and Enceladus as the next priority targets after the in-flight missions. But the Decadal Survey's priorities can shift, and a future survey covering the 2033 to 2042 period could potentially elevate Callisto to a higher priority if JUICE results reveal surprising findings. The scientific community's interest in Callisto has been growing. Several research groups are actively working on models of Callisto's interior, its magnetic induction, its surface chemistry, and its formation history. The number of peer-reviewed papers discussing Callisto science has increased in the years leading up to JUICE's arrival, as scientists prepare for the data that will start coming in the mid-2030s. Callisto is no longer quite as forgotten as it was. Let us now talk about what is perhaps the most philosophically interesting aspect of Callisto, about what it represents as a world that has preserved its past essentially unchanged while everything around it evolved, and what this means for the record it holds. Callisto formed approximately 4.5 billion years ago during the formation of the solar system. In the roughly 4.5 billion years since its formation, its surface has accumulated the record of every significant impactor that struck it. Its dark organic material has been accumulating from the original carbonaceous material and from impactor delivery for the same period. Its ice has been slowly sublimating at the surface, concentrating non-volatile material. The interior has been cooling slowly, generating heat from radioactive decay at a steadily decreasing rate as the radioactive elements have decayed away. The initial post-formation heat has been bleeding into space for 4.5 billion years. Through all of this, Callisto has not been resurfaced, has not been geologically processed, has not been melted and reconstituted. The dark material coating its surface has not been destroyed by volcanism or tectonic recycling. The crater record has not been erased by geological activity. This means that Callisto's surface material, particularly its dark organic component, has been sitting there largely undisturbed for 4.5 billion years. It has been irradiated. It has been struck by impacts that mixed new material in. It has been slowly sublimated and concentrated, but it has not been fundamentally destroyed and recreated. This is extraordinary. Almost nowhere else in the solar system does surface material this old persist intact. Earth's surface is completely recycled by plate tectonics on timescales of hundreds of millions of years. The Moon's ancient highlands are heavily cratered, but have been affected by volcanic flooding in the mare regions. Mars has had geological activity relatively recently. Even the most ancient asteroidal material, the carbonaceous chondrites, has typically been heated and altered during parent body processing. Callisto's surface represents one of the most ancient preserved chemical environments in the solar system. If we want to understand what the organic chemistry of the early outer solar system was like, what was delivered to the early planets by comets and asteroids, what the original chemical inventory of the outer solar system was, Callisto's surface is a preserved sample of that environment, modified by 4.5 billion years of gentle processing, but fundamentally intact. In this sense, Callisto is not a dead world, it is a living museum, a world-sized sample jar containing the ancient chemistry of the solar system's formation era, sitting in the outer solar system waiting to be opened and read. The crater record tells us about impactor populations. The organic chemistry tells us about the original outer solar system volatile inventory. The partially differentiated interior tells us about formation conditions in the Jovian accretion disk. The magnetic induction hints at liquid water maintained under conditions our models struggle to explain. Every one of these pieces of information is ancient. Callisto carries history that no other object we can practically access preserves. This is the strangeness of Callisto that gets lost when it is described as the boring Galilean moon. It is not boring. It is a fossil, a magnificently preserved fossil of the early solar system, sitting at the outermost edge of the Galilean system, dark and ancient and waiting. We have been looking at it from a distance for 4 centuries, ever since Galileo first noted it as a point of light orbiting Jupiter in 1610. We sent spacecraft past it in 1979 and orbited nearby in the late 1990s. We have characterized its surface broadly, measured its gravity, detected its atmospheric trace, and noticed a magnetic anomaly that has not been satisfactorily explained. And in the 2030s, for the first time, we will look at it closely. 21 flybys, multiple instruments, multiple measurements of the magnetic field at different orbital phases, detailed compositional mapping of the surface, better gravity field measurements, high-resolution imaging of terrain we have never seen at this scale. What will we find? The honest scientific answer is that we do not know. Outer solar system bodies have a way of surprising us. Callisto has already surprised us with its magnetic anomaly and its anomalous interior structure. There may be more surprises at smaller scales, in the composition details, in the atmosphere, in the detailed structure of the magnetic induction signature. What we do know is that the simple picture, boring, dead, ancient, unremarkable, is incomplete. Callisto is strange. Stranger than the standard description suggests. Strange in ways that existing data hints at, but does not resolve. Strange in ways that make it scientifically interesting, precisely because the strangeness is unexplained. It orbits at the edge of the Galilean system, farther out, quieter, darker, older in appearance than its dramatic volcanic and tectonic neighbours. It accumulates craters. It holds its ancient chemistry beneath a dark, organic coating. It maintains, possibly, a liquid water layer whose existence our models struggle to account for. It is the forgotten moon. And it is strange. Let us talk about something that requires stepping back from the specific science of Callisto and looking at what it represents in the context of how planetary science as a discipline works, about how decisions get made about which worlds to prioritize, and what the process reveals about the relationship between scientific curiosity and institutional reality. Planetary science in the United States operates on a system of decadal surveys. Every 10 years, the National Academies of Sciences, Engineering and Medicine convenes a committee of planetary scientists to assess the state of the field, identify the most important scientific questions, and recommend a prioritized list of missions for the coming decade. These recommendations carry significant weight with NASA and with Congress in allocating funding. The most recent decadal survey, Planetary Science and Astrobiology Decadal Survey 2023 to 2032, published in 2022, recommended as its highest priority flagship mission a Uranus orbiter and probe. Its second priority was a mission to the ocean world Enceladus. Mars sample return, already in progress, was a third major priority. The Jovian system, and specifically the Galilean moons, appear in the survey primarily through the in-flight missions, Europa Clipper and JUICE, that are already operating or launched. A dedicated Callisto mission does not appear as a priority recommendation. The scientific community has, collectively, ranked other destinations as more urgent. This is not unreasonable, given the scientific arguments. Europa's subsurface ocean has stronger evidence and better characterized heat sources. Enceladus actively vents material from its ocean into space, making it possible to sample the ocean without landing. Uranus has never had a dedicated orbiter. These are strong scientific cases, but the process reveals something about how scientific priorities work. Callisto's strangeness, its magnetic anomaly, its undifferentiated interior, its complex organic surface, is known to the community. Papers have been written about it. Scientists have argued for its scientific value. Yet the community consensus has consistently placed it below other targets. Part of this is the comparison problem. When you have to rank destinations against each other, Callisto consistently loses to Europa on the question of subsurface ocean science. Europa's ocean is better established and has more compelling characteristics. It loses to Ganymede on magnetic field science. Ganymede's intrinsic magnetic field is more dramatic and better understood. It loses to Io on geological activity science. Io's volcanism is the most dramatic in the solar system. Callisto's scientific interest is real, but distributed across multiple questions, none of which is as singularly compelling as Europa's ocean or Io's volcanism. A world that is interesting in many moderate ways often loses out to worlds that are extremely interesting in one specific way. This is a structural feature of how scientific prioritization works. It favors dramatic, singular phenomena over distributed, moderate complexity. Whether this is the right approach for understanding the solar system as a whole is a genuine question that scientists debate. There is an argument that understanding Callisto's formation history, and specifically why it is undifferentiated while Ganymede is differentiated, is as scientifically fundamental as understanding Europa's ocean. The formation of the Galilean moons is a test case for models of giant planet system formation. Getting that test case right requires understanding all 4 moons, not just the most dramatically interesting ones. Callisto's anomalous interior is a constraint on those formation models that cannot be explained away by focusing only on the inner moons. Let us now talk about what the specific composition of the dark material on Callisto's surface can tell us about the history of organic chemistry in the outer solar system, because this is an underappreciated aspect of Callisto's scientific value. The outer solar system formed from material that was significantly enriched in carbon relative to the inner solar system. The carbonaceous chondrite meteorites, which sample the composition of outer asteroid belt material, contain up to several % by mass of carbon in various organic forms. Comets contain even higher proportions of complex organic material. The Kuiper belt objects and outer planet moons formed from material even more enriched in carbon-rich compounds. Callisto, having formed in the outer Jovian accretion disk, incorporated a significant fraction of this carbonaceous material. Unlike the inner Galilean moons, where intense tidal heating has driven off volatile organic material, Callisto has retained and concentrated its organic inventory over the age of the solar system. The dark lag deposit on Callisto's surface is the result of sublimation concentrating this material, ice evaporating and leaving behind the non-volatile carbonaceous residue. Over billions of years, this concentration has produced a layer of material that is, by mass fraction, highly enriched in complex organics relative to the original accreting mixture. What exactly is in this concentrated organic residue? The spectroscopic data we have is suggestive, but not definitive. The infrared absorptions observed are consistent with complex carbonaceous material, but cannot distinguish between many possible specific compounds without better spectral resolution. The dark material absorbs sunlight broadly and does not show the specific sharp absorption features that would allow unambiguous molecular identification with current data. But what could be there based on what we know about organic chemistry in the outer solar system? Polycyclic aromatic hydrocarbons, PAHs, are a ubiquitous class of organic compound in space. They are detected in the interstellar medium, in carbonaceous meteorites, in comet material. They are produced by the ultraviolet and cosmic ray processing of simpler organic material over long timescales. They are stable enough to survive the radiation environment even over billions of years. Aniphatic hydrocarbons, longer chain carbon compounds, are also expected. These are less stable under radiation than PAHs, but are abundant in the initial organic inventory and continuously delivered by comets. More interesting from a prebiotic chemistry standpoint are nitrogenous compounds. Amino acids have been detected in carbonaceous meteorites, including some amino acids not found in biology, suggesting they are produced by abiotic chemistry. Nucleobases, the building blocks of DNA and RNA, have also been detected in meteorites. If the original organic material that accreted into Callisto included these compounds, the surface could contain amino acid precursors and nucleobase analogues after billions of years of radiation processing. The detection of glycine in the cometary material returned by the Stardust mission and confirmed in the coma of Comet Wild 2 is particularly relevant. Glycine is the simplest amino acid. Its presence in cometary material suggests it is present in the general inventory of outer solar system organics. Callisto accreted from material similar to comets. It should have incorporated glycine and other amino acids in its original composition. What happened to these amino acids over 4.5 billion years of radiation processing? They could have been destroyed. Amino acids are radiation sensitive, and long-term cosmic ray bombardment could have broken them down. They could have been modified. Radiation can both destroy and create organic molecules, depending on conditions. The irradiation products of amino acids in icy matrices include more complex compounds that, in some cases, are more radiation stable than the precursors. The net result after 4.5 billion years of slow radiation processing in Callisto's outer solar system environment is genuinely unknown. It is a chemistry experiment that has been running for the age of the solar system, and whose results we have not yet read. Reading those results, characterizing the specific organic inventory of Callisto's surface at the molecular level, would be transformative for understanding the organic chemistry of the early solar system and what kinds of prebiotic chemistry are accessible in outer solar system environments. Let us now talk about something that is active and uncertain, about the specific question of whether Callisto's induced magnetic field could have an explanation other than a subsurface ocean, and what constraining this uncertainty requires. The Galileo magnetic field measurements during Callisto flybys showed an anomaly in Jupiter's field near Callisto that was best explained by an induced magnetic field, a field generated inside Callisto in response to the time-varying component of Jupiter's field. The same type of induction signal was observed at Europa and Ganymede, and subsequent observations, particularly Hubble observations of Ganymede's auroras, have confirmed that the induction interpretation is correct for those moons, indicating subsurface conducting layers, that is, oceans. For Callisto, the evidence is less clear. The Galileo Callisto flybys were fewer in number and covered a more limited range of orbital phases compared to the Europa and Ganymede flybys. The induction signal detected is real, it is in the data, but its interpretation is more ambiguous. The primary alternative to a subsurface ocean as the source of the induction signal is conducting material in the surface regolith. If the surface layer contains sufficient amounts of electrically conducting material, for example salts or metallic particles delivered by impactors, it could, in principle, generate a near-surface induction signal that mimics the deeper signal from a subsurface ocean. However, the properties required of a surface conducting layer to explain the Callisto signal are somewhat extreme. The layer would need to be thick and highly conducting in a way that is not easily reconciled with what we know about the surface composition. The subsurface ocean interpretation remains more natural. What would definitively distinguish between a surface layer and a subsurface ocean? Multiple measurements of the induction signal at different orbital phases of Jupiter. The inducing field from Jupiter changes as Jupiter rotates. The component of Jupiter's tilted magnetic field that passes through Callisto varies with Jupiter's 10-hour rotation period. An induction signal from a deep subsurface ocean would show a specific relationship to this periodic variation. A signal from a very shallow surface layer would show a different phase relationship. With only 6 flybys and limited orbital phase coverage, Galileo could not fully characterize this phase relationship. JUICE's 21 flybys, distributed across multiple Jupiter rotations and at varying orbital geometries, will provide the measurements needed to distinguish between these interpretations. If JUICE confirms the deep induction signal consistent with a subsurface ocean, the scientific community will have to take Callisto's ocean much more seriously and devote significant theoretical attention to explaining its existence and maintenance. If JUICE finds a signal more consistent with shallow surface conducting material, it will resolve the ocean question in the negative and redirect Callisto science toward other questions. Either outcome is scientifically valuable. Science advances through resolved questions as much as through new discoveries. Let us now talk about Callisto's relationship to the question of water in the outer solar system, about how the presence or absence of a Callisto ocean fits into the broader inventory of liquid water beyond the asteroid belt. 20 years ago, the idea that liquid water existed in the outer solar system was speculative. Earth was the only world known to have liquid water. The possibility of Europa's subsurface ocean was scientifically motivated by the tidal heating argument and the surface geology, but it was not confirmed. Enceladus had not yet revealed its plumes. Titan's hydrocarbon lakes were not yet discovered. In the intervening 2 decades, the picture has changed dramatically. Europa's ocean is now broadly accepted by the planetary science community, with the induced magnetic field and the surface geology both pointing strongly to it. Enceladus's ocean has been confirmed through direct sampling. Cassini flew through the water plumes and measured their composition, including salts and organics consistent with a saline ocean in contact with a rocky sea floor. Ganymede's ocean is now accepted based on the Hubble auroral observations and the magnetic induction. Titan has a likely subsurface water-ammonia ocean beneath its hydrocarbon surface layers, evidenced by the Schumann resonances detected by Huygens and by the tidal deformation measured by Cassini. Pluto may have a subsurface ocean. Models of its interior suggest that the heat of formation and radioactive decay could maintain liquid water beneath its ice shell, and New Horizons observations of Pluto's geology have been interpreted as consistent with this. Ceres, the largest body in the asteroid belt, shows evidence of brine pockets and possibly a subsurface liquid layer from dawn observations and recent Hubble observations of bright spots associated with salt deposits. The outer solar system appears to be hydrologically active in ways not anticipated by early models. Liquid water, the solvent most associated with life on Earth, may be more common in the outer solar system than it is in the inner solar system. Callisto's possible ocean, if confirmed, would add another data point to this inventory. It would extend the range of bodies harbouring liquid water to include a partially differentiated world with minimal tidal heating, suggesting that the conditions for maintaining subsurface water are even broader than current models predict. This matters for astrobiology at the broadest level. If liquid water can persist in a world with Callisto's limited heat sources, then the number of ocean worlds in the outer solar system, and by extension in other planetary systems, may be larger than estimates based on tidal heating alone would suggest. Subsurface water sustained by radioactive decay and antifreeze compounds like ammonia rather than by tidal heating could be common in the outer solar system and in the outer regions of other stellar systems. The inventory of liquid water in the solar system is one of the most important inputs to estimates of where and how frequently life might arise. Getting that inventory right, including Callisto's ambiguous contribution to it, is scientifically significant beyond the specific question of whether Callisto itself is habitable. Let us now talk about the specific challenge of what a mission to Callisto would actually need to do to resolve the key open questions about what measurements are necessary and what those measurements would cost in engineering and mission design terms. To confirm or refute the subsurface ocean hypothesis, a mission would need multiple passes over Callisto, with magnetometers capable of measuring the induced field at different orbital phases of Jupiter. As discussed, JUICE will provide this. But if JUICE's magnetic measurements are ambiguous, if the data does not cleanly distinguish ocean from surface conducting layer, a follow-up mission with more orbital phase coverage and closer approach distances would be needed. A dedicated Callisto orbiter could provide sustained orbital coverage, not just flybys, but continuous observation from a stable orbit. An orbit at a few hundred kilometers altitude would allow high-resolution imaging of the entire surface, compositional mapping at fine spatial scales, detailed gravity field mapping to improve the moment of inertia determination, and sustained magnetometer coverage through multiple Jupiter rotation periods. The surface composition question, characterizing the organic material at the molecular level, would be best addressed by a combination of an orbital spectrograph with high spectral resolution and an in situ measurement. A lander, or even a simple impactor that kicked up surface material and allowed analysis of the resulting cloud by an orbital spectrograph, could dramatically improve the compositional characterization. The atmosphere question could be addressed from orbit with a mass spectrometer capable of detecting trace species at the parts per billion level or better. Such an instrument, sampling the thin exosphere during low-altitude orbital passes, could identify specific molecular species that the surface spectroscopy cannot distinguish. The interior structure question, why Callisto is undifferentiated, would benefit from seismology. Seismometers on the surface could detect tidal oscillations from Jupiter's gravity field, whose amplitude and frequency would constrain the interior structure. They could detect any low-level internal activity, if it exists. Seismology has transformed our understanding of the Moon and Mars through the Apollo seismometers and the InSight lander, respectively. The same approach applied to Callisto would be transformative. The cost of a dedicated Callisto orbiter mission, analogous in concept to Europa Clipper or Cassini, would be in the range of $2 to $3 billion at current mission cost levels. A lander would add substantially to this cost. These are not small investments, and they would need to compete with other planetary science priorities in the decadal survey process. The case for making that investment rests on the scientific questions that only Callisto can answer. The formation history of the Galilean moons, the organic chemistry archive of the early outer solar system, the magnetic interior mystery, the distribution of liquid water in the outer solar system. These are genuine scientific questions. Their answers are unknown. The answers would matter to our understanding of the solar system, and potentially to our understanding of where life might arise. Callisto is the key to some of those answers, not because it is the most dramatic or the most accessible world, but because it preserves a record that no other accessible world preserves. Let us now talk about something that grounds all of this in the simplest possible terms, about what you would actually see if you could stand on Callisto's surface and look around. The first thing you would notice is the sky. Jupiter dominates it. From Callisto's surface, Jupiter subtends approximately 10.7 degrees across the sky, about 21 times the angular diameter of the Moon as seen from Earth. This is not a point of light. This is a vast banded sphere filling a significant fraction of the sky. The cloud bands are visible, the alternating light and dark zones. The Great Red Spot would be visible when it faces Callisto's position. The 4 Galilean moons, including Callisto itself, you would be on one of them, appear as brighter points of light moving noticeably against the stellar background. Find Jupiter tonight. If you don't know where it is, look it up. It takes 30 seconds. It is usually the brightest, steady point in the sky, cream white, not flickering the way stars flicker. Look at it. What you are seeing is a planet 11 times the diameter of Earth, 318 times its mass, with a storm system larger than our entire planet that has been rotating continuously for at least 350 years. You are seeing it from somewhere between 588 million and 968 million kilometers away, depending on where Earth and Jupiter are in their orbits tonight. The light reaching your eye left Jupiter between 33 and 54 minutes ago, and orbiting that planet, invisible to the naked eye, are 4 large moons that Galileo Galilei first noticed on January 7th, 1610, as 4 small points of light positioned near Jupiter and changing their positions from night to night. The outermost of those 4 moons is Callisto. It orbits at 1,882,700 kilometers from Jupiter's center. It has been orbiting there for approximately 4.5 billion years. Its surface is the most heavily cratered terrain in the solar system, an unbroken record of impacts accumulated without geological erasure since the solar system was young. Every crater on its surface is a document, a record of something that hit it at a specific time, at a specific velocity, at a specific angle, and was absorbed and preserved. Nothing has erased those craters. No volcanism, no tectonic activity, no global ocean flooding the lowlands. Just accumulation, undisturbed for 4 billion years. The dark material coating that surface, the carbonaceous organic compounds that sublimation erosion has concentrated into the terrain, began accumulating when the solar system formed. It has been processed by cosmic rays and slow ultraviolet bombardment, and Jupiter's attenuated radiation for 4.5 billion years. It contains chemistry that no other readily accessible object in the solar system preserves intact. The organic inventory of the early outer solar system, sitting there, ancient, concentrated, unread. Beneath that surface, somewhere at uncertain depth, with uncertain confidence, there may be liquid water. Not from tidal heating as in Europa, not from a clear, well-understood heat source, from something our models struggle to specify. The Galileo spacecraft measured a distortion in Jupiter's magnetic field near Callisto that is most naturally explained by a conducting layer inside the moon, and the most natural conductor is salty liquid water. Why that water remains liquid when the heat sources seem insufficient, we do not know. The ammonia hypothesis helps, but does not fully resolve it. The undifferentiated interior of Callisto, which the gravity measurements suggest, but which our formation models do not fully predict, adds another layer of uncertainty. A world that should have separated into rock and ice layers over billions of years, apparently has not. The rocky and icy material remains mixed in ways that do not fit the standard picture of how large icy moons evolve. 2 observations, 2 anomalies, neither fully explained. The standard description of Callisto is the boring one, the dead one, the ancient cratered ball at the outside of the Galilean system that lacks the drama of Io's volcanoes, or the astrobiological excitement of Europa's ocean, or the sheer scale of Ganymede. That description is incomplete. Callisto is strange. Strange in specific, measurable, quantified ways that existing data establishes and does not explain. Strange in the way that scientific anomalies are strange. Not dramatically, not photogenically, but persistently, in the numbers that do not quite fit the models. In 2031, the JUICE spacecraft will arrive at the Jovian system after a journey of 8 years from Earth. In the years that follow, it will fly past Callisto 21 times. Each flyby will return magnetic field measurements, compositional spectra, gravity field data, images at resolutions we have never had. 21 times the data we got from Galileo's 6 flybys. What will it find? The honest answer is that we do not know. The outer solar system has a consistent record of surprising us. Io's volcanism was not predicted. Enceladus's geysers were not predicted. Titan's methane lakes were not predicted. Pluto's mountains and nitrogen plains were not predicted. The track record of outer solar system bodies, when examined closely, is a track record of being stranger than expected. Callisto may confirm the subsurface ocean and deepen the mystery of what maintains it. It may reveal unexpected organic complexity on the surface. It may show terrain features at high resolution that change our understanding of its geological history. It may do something else entirely that we have not anticipated. Or, JUICE may find that the magnetic anomaly has a mundane explanation, that the organic surface is simpler than hoped, that Callisto is, in the end, closer to the boring description than the strange one. We will find out. In the mid-2030s, the data will come. But what is already true, what the existing data already establishes, is that Callisto does not deserve the dismissal it has received. The forgotten moon, the boring Galilean, the one nobody talks about. These descriptions are based on comparison with the more obviously dramatic inner moons. They are not based on Callisto being understood and found ordinary. They are based on Callisto being insufficiently examined. The most heavily cratered surface in the solar system, a magnetic anomaly suggesting a subsurface ocean without a clear heat source, an interior that refused to differentiate over 4 billion years in ways our models do not fully explain. A surface coating of ancient organic chemistry 4.5 billion years in the making. These are not the features of a boring world. They are the features of a world we have not looked at carefully enough. Look at Jupiter tonight. It is there, bright and steady in the sky. To the left or right of it, depending on the date, Callisto is somewhere in its 16.7-day orbit, invisible to the naked eye, dark against the darkness. Ancient, cratered, strange, the forgotten moon. Still out there, still waiting.